let us now talk about heterogeneous equilibrium. So, last class we understood homogeneous equilibrium. Now, what is heterogeneous equilibrium? Heterogeneous equilibrium is a condition where the equilibrium is in a system which has got more than one phase. If all the reactants and products are in the same phase and equilibrium is achieved, we call it as homogeneous. If there is a reactant and a product, if they are existing in more than one phase and you achieve an equilibrium in that state, in that system, such an equilibrium is said to be heterogeneous equilibrium. Example, water in its liquid state in equilibrium with water gaseous stage. Look at that, the states are different and this is said to be a heterogeneous equilibrium. Or another example, if you have calcium hydroxide which is a solid and let us say it is in equilibrium with its saturated solution. So we have a lot of water, saturated solution I mean. So you are going to get, there is an equilibrium between the ions of calcium oxide. That is, what happens if you are taking calcium oxide and trying to dissolve it in water? That's, you are preparing a saturated solution of this. In a saturated solution, now this should be a saturated solution. A saturated solution of calcium hydroxide, which is a solid, is in a state of equilibrium with its ions, that is calcium ions, aqueous, and hydroxyl ions, which are also aqueous. Why it is heterogeneous? Because this is in a solid state, these two are in aqueous state. Okay, now when I say whenever we talk about heterogeneous equilibrium, we have to understand a few things. Alright, so whenever we talk about heterogeneous and you have pure solids or liquids, its concentration of pure solids and liquids, what is concentration? Amount present in a solution, that is kind of fixed. This part you should this is what you need to remember. Okay, and this is very important when we are talking about heterogeneous equilibrium. You are talking about pure solids and liquids, gases, no nothing like that. Okay, so for pure solids, and you will understand eventually when I am doing it, but for a pure solid and liquids, the concentration is fixed. What is the meaning of that? If I talk about molar concentration, what is molar concentration? Number of moles in unit volume, right? Or 1 liter for that matter. Right, so now it is similar to density. You know what is density? If you take 1000 liters of water, you take 2000 liters of water, density is fixed. Why? Because it's mass per unit volume. Similarly, it is independent of the amount. So I should say this word. I think then it makes sense to you. It is independent of the amount of substance. Like for example, concentration, molar concentration, let us say you are taking 1 centimeter of water, pure water, it will be equal to any concentration, any volume. You take 1000 cm cube of pure water, it is the same. Just like how density is same, because here it is number of per unit volume. Even if you increase the volume, okay, this is number of moles divided by unit, it's like 1 liter, that's the definition of 1 mole, right? Molarity is nothing but number of moles in 1 liter of a solution. So even if you increase anything, the number of moles will, if volume is increased, the number of moles will also decrease by the same amount, such that this is constant. So this is the most important thing you need to remember in case of heterogeneous equilibrium. When you are talking about pure solids and liquids, its concentration is fixed, or in other words, it is independent of the amount or the mass, how much you take, 1 gram, 10 gram, 15 gram. So you don't have to specify its concentration. Alright, so as a key pointer to you, if I have to simply say this so that you remember it well, for solids and liquids, okay, solids and liquids, it is insignificant. What is insignificant? The concentration is insignificant. It doesn't matter, because it is fixed. We don't have to worry about it. Okay, that is what I mean. So you do not consider this. But if you are talking about gas and aqueous, it varies. The concentration will change over the as and when the reaction proceeds, and it becomes significant. So imagine you have some gaseous, some solids and gas and liquids and aqueous. Imagine you have everything in a reaction. Solids, its concentration will not change over a period of time, because now don't get confused when I say concentration. You might say that I took 100 gram of this and it reacted and I'm only left out with 20 grams or something. I am not talking about the in terms of number of moles. I am talking about molar concentration, that is number of moles per unit volume. That will be fixed, and since that is fixed, we don't have to worry about it because it's not going to change at all. But what happens in gaseous and aqueous states, the molar concentration, that is concentration per unit volume, that changes, and that is why it becomes very, very significant. So, and that has to be considered. So this you don't have to bother. This is something that you have to bother. Okay, let me take an example. The decomposition of calcium carbonate, which is in solid, giving you calcium oxide, which is solid, plus carbon dioxide gas, which is in the gaseous state. Okay, so actually how you write the equilibrium constant? It's the concentration of the product of the products, okay, raised to their stoichiometric ratios, divided by the product of the concentration of reactants raised to their stoichiometric coefficients. Now if I write the states here, okay, so this and this becomes insignificant because it's not gonna change, right? So I don't want to worry about it. So now the final Kc will be just the concentration of carbon dioxide, which is in the gaseous state, or in terms of Kp when I write, it is nothing but the partial pressure of carbon dioxide gas. Okay, now if you carefully observe this, Kc, what will be the unit in this case? Concentration, it will be mole, right? It will be, the concentration will be mole per liter, whatever you say, mole per liter if you are taking about a molarity here. And here it will be bar because it's a pressure. But they are constants, and the definition says is the product of the concentration of something by concentration of something. So technically it should not have any units, they are dimensionless. But in this case we are getting some dimensions. If you calculate in terms of concentration, you are getting moles per liter. If you are calculating in terms of pressure, you are getting bar. Okay, now just to make sure that it is dimensionless, what we do here is, whenever you say, and we always carry out it at constant temperature, correct? So at constant temperature, let us say at 1100 Kelvin, the pressure of carbon dioxide is going to be 2 into 10 power 5 Pascal. If this is the case, what it means that at this temperature, because the pressure is this much, you can also say that there is a constant concentration of this gas in equilibrium with these two. Or in other words, when this reaction is in equilibrium at this particular temperature, that means if I say pressure is something, I can also say there is some constant. The pressure is now constant, right? I can also say that concentration of carbon dioxide is also some constant. I can say that, correct? So now how do I write Kp? Kp will be that is PCO2, which we have just written it here, and at this temperature its value is 2 into 10 power 5 bars. So to remove this, because we do not want the dimensions, I divide by 1 bar, which is, so this should be in pascals. Sorry, it's not in bars, it's in Pascal. Okay, so you divide by Pascal. The reason why do we do it is, we try to write everything in its standard states. Okay, so if you want Kp or Kc to be dimensionless, that is no units, we have to consider that the reactants and products should be in their standard state. And when I say standard state, what do you mean by that? The pressure is 1 bar or 10 power 5 Pascal, and concentration will be 1 molar. So that's the reason when we try to look at that, if we do not consider standard state, then it will have a unit. So when we say that reactant or product in its standard state, it will be at 1 bar pressure. So you will divide it by 1 bar. So now it will be, this will get cancelled. It is just going to be 2. Okay, so we say that Kp is 2 here. It is no longer in terms of pressure. It is now a dimensionless unit. And to make sure it is dimensionless, it can be Kp or Kc. If it was Kc, you will divide by 1 mole. You will get something in terms of mole per liter. You will divide it by 1 mole, which is nothing but mole per liter again, right? Molar, or in other words, yes. This is not mole, molar. This is how we write, right? 1 capital M is molar, which is mole per liter. Alright, so just to make sure that your Kp and Kc doesn't have a unit, you make sure that the reactants products are in standard state. Pressure at standard state is 1 bar, concentration is 1 molar. Okay, only when you do that it becomes dimensionless. Okay, let us say, for example, I'll take one reaction so that you understand this even more better. If you have N2O4, which is a gas, okay, and then you say that it is in equilibrium with NO2 gas, what will its concentration be in terms of equilibrium constant in terms of concentration? It will be NO2 whole power 2 divided by N2O4. Correct? So this is also in gas, this is also in gas. So we cannot ignore anything. Now, if you are talking about dimension as such, this is mole per, this what will be dimensionally mole square per liter square, and here it will be mole per liter because it's square here. So dimension wise this Kp will have mole per liter if you're talking in terms of concentration. Kp will be as per the units, it will have something bar, and we do not want that. So that's the reason what we do here is we divide it by the, we try to represent it in its standard state. So for example, if you say you have a P of some gas, let us say we say it is 4 bar. We always try to write 4 bar divided by 1 bar. So now it is just 4. So we say that Kp is this your Kp. Kp in terms of pressure will be just 4, doesn't have a unit. Okay, so that's the reason we consider it this way. Whenever we feel that there is a unit, we always try to write it in its standard state. So whenever you write, you divide by 1 bar, the bar will go and it becomes dimensionless. If it's concentration, we try to write it in terms of divide it by 1 molar, that is mole per liter. Okay, now one more, let us talk about purification. If you are talking about purification, like nickel, when it is reacting with carbon monoxide, nickel is a solid, this is a gas, to give you nickel carbonyl. This is nickel carbonyl, which is a gas. Okay, now if you're talking about this reaction, what you need to consider here? This I don't have to consider because it's a solid. The concentration is fixed, it does not vary, so it's insignificant. We will just take nickel carbonyl's concentration divided by carbon monoxide concentration raised to the power 4. Okay, so we are not going to consider this. And again, if you look at it, this will be mole per liter, right? And this will be again mole per liter raised to the power 4. Correct? So now you have to convert it back to by representing in the standard state, which we will do in the new variables. Okay, so another example will be if you have Ag2O plus nitric acid. Now this is a solid, this is an aqueous, to give you silver nitrate, 2 moles of silver nitrate in aqueous plus H2O in liquid. This is insignificant, pure liquid, pure solid. So what will your Kc be here? Silver nitrate concentration raised to the power 2 because of its stoichiometric coefficient. Concentration of nitric acid raised to the power 2. This and this becomes insignificant. Okay, let us take up one numerical to actually understand heterogeneous equilibrium. And I am going to do 7.6 of your worked example. Okay, so what is it telling you? There is a reaction given to you. Carbon dioxide plus carbon, the solid, that is graphite, giving you carbon monoxide. 2 moles of carbon monoxide, which is a gas. Okay, so this is the reaction that is given to you. and Kp for this reaction is 3, that's given to you at 1000 Kelvin. It's the temperature. If initially, you can just read the question in your textbook. If initially P pressure, partial pressure of carbon dioxide was 0.48 bars initially, P carbon monoxide is 0 bar. Obvious, because initially there will be no product, so no partial pressure. And they say that pure graphite is present. That means we do not need its pressure or concentration. It is insignificant. You have to calculate the equilibrium partial pressures. So pressure at equilibrium, this is initial what is given. At equilibrium, what will be the pressure of carbon monoxide and carbon dioxide? Okay, so let us consider this reaction. So this is the given reaction, giving you 2 moles of carbon monoxide gas. Now this becomes insignificant, that's the reason nothing is given. Let us write initial condition and then let us write equilibrium condition. So initially the pressure of this was 0.48 bar and obviously this is 0 bars. Okay, let us now understand, initially there was some pressure and eventually when the reaction is proceeding, some of it is converted into carbon monoxide, correct? So if in terms of moles we say X moles got converted into carbon monoxide, the pressure of the carbon dioxide will be lesser. Why? Because there is, now what is pressure? Pressure is basically created because of the collision. Now if there are more molecules, more moles, there will be more collision. So more pressure. Now initially it was 4.48 bar of pressure. That is for carbon dioxide. Now little bit of carbon dioxide is converted into carbon monoxide. Its pressure at equilibrium will be reduced for this. And here it will be greater because initially 0. There was no carbon monoxide, no pressure. When it is formed, it will have pressure. So if you say X is the decrease in pressure, okay, of carbon dioxide. Reason, because it is converted into carbon monoxide. Okay, because carbon dioxide is getting converted into carbon monoxide, let us say X is the decrease in the pressure of carbon dioxide. So what it will be at equilibrium? X is the decrease. So equilibrium pressure will be 0.8 minus X. For 1 mole you are getting 2 moles. For these many moles, how many? What will be the pressure? It will be 2x. Because 1 mole is giving you the same pressure, correct? So these many moles, that is for 1 mole of carbon dioxide. For 1 mole of carbon dioxide, 0.48 minus X will be the pressure of carbon dioxide and X will be the pressure of carbon monoxide. But since we have 2 moles, instead of X it will be 2x. Okay, so now let us calculate Kp. I'm not doing all the calculation. So anyway, so this is just going to be carbon monoxide 2. We're talking about pressure. So it will be pressure of carbon monoxide, partial pressure raised to the power 2 divided by partial pressure of carbon dioxide. And this is given to you as 3. Kp is given to you as 3. This will be 2x whole square divided by 0.48 minus x. So if you just rearrange this, you will get a quadratic 4x square plus 3x minus 1.44 is equal to 0. If you solve it using quadratic formula, you are going to get minus 3 plus or minus 5.66 by 8. I'm not doing the calculation because it's time consuming and anyway you know it. If there is any concern, you can ask me. But yes, now the negative side we are going to neglect. Okay, negative, neglect. So what will be x? Minus 3 plus 5.66 by 8 and that is going to be 0.33. Okay, so I got my x, which means that at equilibrium, the pressure of carbon dioxide, what is it? 0.48 minus x or 0.48 minus 0.33 and that is going to be 0.15 bar. That is at equilibrium. Okay, and partial pressure of carbon monoxide at equilibrium is 2x. So it is going to be 2 into 0.33 or 0.66 bar.